Hi, in today's lecture I will discuss about the power losses in BJTs, in power BJTs, you can say it. So firstly, I will be discussing some formulas about the currents and the power losses of power BJT in the on-off state as well as in the switching state. So first to remember is this formula, which is the output current in the power BJT, which is IC, and for that we have to keep into consideration the VCC, the biasing voltage, minus the output voltage divided by the collector resistance, and we can also calculate its maximum value by taking this expression which involves VCC and RC. And for the common base configuration of this power BJT, we can calculate the value of IB by this formula, which involves the beta current gain in the common base configuration, and the IC, which is the output current, we can calculate its ratio, and we can observe the value of IB, and same we can do the calculation of VCC, the biasing voltage, and the collector resistance along with beta. When we calculate this ratio, we can also calculate the value of IB. So we can also have to understand these characteristics of the power BJT, where we have the output current on the y-axis, the output voltage on the x-axis, and then we have a load line which is defining the operation of some power BJT over here. Now we can observe some uh, formulas of losses on the base of the power BJT. If you can see the figure which I will show you over here, you can see that figure. If we have this figure, then you can see we have, this is power BJT. Here we have base, above collector, and below emitter, and we can calculate the different losses at different terminals. And for that I am I am giving you this formula, that we have the loss at the base terminal is can be calculated by input voltage multiplied by the base current, while at the loss at the collector terminal can be calculated by multiplying the output voltage with the output current. So we have two formulas, and then we have also the formula of the on state power loss, which can be calculated by adding the above two values over here. And as we already know that the value of this one is very much negligible, so the loss at the base terminal is very much negligible, so uh, we can subtract that value, or we can remove that value, and we just can calculate the on state power loss in the power BJT by this expression only, which will give the nearly approximate or accurate value of the loss in the power BJT in the on state. Then we have the off state power calculations, where we have the output voltage, which is the collector to emitter voltage, multiplied by the output current, which is IC, and which is sometimes being said as leakage current in the off state, because in the off state a very small amount of negligible current will be passing from emitter collector, between emitter collector terminals of the power BJT. So we have formula for the energy loss in the on state over here, where we have the biasing voltage, output biasing voltage multiplied by the maximum value of the collector current divided by 6 multiplied by the switching on time. And then we have the off state energy loss formula, which is the same, and over here we have the off to on state time, and here we have the on to off state time. So when we uh, are having all these calculations happened, the on state power loss, the off state power loss, the energy loss from the on to off state and from the off to on state, then we can summate all these values, and we can have the on state power loss multiply by the T on time to get the on state energy loss, and for the off state energy loss we multiply the P power loss during the off state multiply by the off time to calculate the off state energy loss. And then for the switching on and switching off, we have already calculated from these formulas. When we multiply those with the frequency of operation of the power BJT, we are able to calculate the power loss, which is the average power loss in the whole power BJT. So now we have to do some three numericals to use these above formulas, and for that firstly we will be doing this example, which is saying that in the figure 3.4, which is over here, this figure it is talking about, this is the figure, I can put it over here for a small duration of time, that in that figure he is saying if we have the biasing voltage can be 120 volt, the collector resistance is 20 ohm, and the VI characteristics of this whole arrangement is being shown in the figure 3.5, which is this figure. If you can, I can put this below, then this is the figure which is giving us the output current on the y-axis, the output voltage on the x-axis, and then we have some characteristics based on different input current values, which is IB, and the load line is telling us about the operation region of that device. So it is saying that if we have all these values, we have the figure, we have the characteristics, we have to calculate the power loss for different base current values, and we are over here given the base current values. So what we will be doing, we will be calculating the load current, which is the IC, and we will be calculating the power losses uh, for that. So we have two formulas. The first one is this, by which we can able to calculate the load current, and for the power loss we have which formula, which we have is this formula we have over here, and or we can use this formula. So in both cases we have nearly the same formula to calculate the power losses over there. So what we will do firstly is that we have this VCC value, we have this RC value, we have to observe the value of VCE from the uh, VI characteristics, which is shown over here. And if we see that we have zero point 0.6 value of base current over here, for that we have what value of VCE, it is nearly observing about one value, VCE is 1 volt over here. So from the figure we have analyzed that when IB is equal to zero point 0.6 ampere, then VCE is equal to 1 volt, and we putting this value in the formula to calculate the value of output current, which is 5.95 ampere, multiplying that value with the above value to calculate the power loss over here. Similarly we are doing it for all remaining. We are taking this value, we are looking for that value on the load line of the this graph over here. Example, we have also we have the same case over here where we have to see that value, the figure, this figure over here, and we have different values. The VCC biasing voltage value is given to us, the RC value is also there, the VCE, which is the output voltage value, is also given over here, and the input voltage VBE value is also over here, as we have the common base configuration, and we have the relevant current gain value also over here. So we are to find the value of IC which can be calculated by this formula by putting all the relevant values which are given to us, and it is 10.36 ampere. As it is the common base configuration, the value of IB depends upon this ratio, putting the relevant values of IC calculated earlier over here and the beta, which is the current gain in the common base configuration, to calculate the value of IB, which is the input current. And then we have to calculate the values of losses of power at the collector and the base terminal. For that we have this formula to calculate the base of the power loss at the collector terminal, and we can see value of VCC given to us. RC value is also there over here, and we have the switching off time over here, and we have the frequency of operation of the device, from which we can calculate the time period of operation. So we have to calculate these three values: the turn off energy loss, the turn off energy loss, turn on energy loss, and the switching power loss. So we already know that when we have switching on energy loss, then its formula is given in the start. We have studied, we have this formula, and for the switching off energy loss we have this formula, and here we have the value of IC max, which can be calculated by the expression which we have studied earlier. This one is the formula by which we can calculate the value of IC, its maximum value. So what we are doing over here is that we are firstly calculating the value of IC max by putting the value of the biasing voltage, which is VCC, and then RC. Then we have the value of IC max is 10 ampere over here. And then what we are doing over here, we are using the formula of the switching on energy loss. We are putting the value of this IC over here, the VCC over here, divided by 6, multiply by the uh, you can see over here the turn switching on time over here, which is this one value, and for the to calculate the switching off energy loss, we are putting the value of this one over here, and the other values are the same. So by these two formulas we are able to calculate the energy losses during the switching on and switching off operation. So the total energy which is being lost due to during the switching operation will be the summation of these two values, which is this one over here, and when we multiply it with the frequency of operation of the device, then it will be able to give us the switching power loss. Thank you very much.